like number theory over integers, which is counting primes in arithmetic progressions. So we'll take a number q, a residue class mod q, which is relatively prime to q, and x a real number. And we can look at the number of primes less than x congruent to a modulo q. And as typically, for any problem of this type involving counting primes, you can make a slightly nicer problem with slightly nicer formulas by replacing the primes with the von Mankel function. So in this case, the von Mankel function of a natural number n is defined to be log p if n is a power of a prime p, power of exponent at least 1, and 0 if n is not a prime power. And then summing for n less than x congruent to a mod q, the von Mankel function of n is basically equivalent to counting primes. You can go back and forth between the two problems very easily, but it'll lead to slightly nicer formulas. So that's what I want to talk about. So there's one very natural kind of central approach to this problem, which is by Fourier analysis on the multiplicative group mod q. So what we're going to do is we're going to take our sum over n congruent to a mod q and write it as an average over characters chi from the multiplicative group mod q to the complex numbers of the sum of lambda, the von Mankel function, against chi, at least over numbers relative prime to q. And to make this work, we have to twist the average by the conjugate character evaluated a, and then by the Fourier inversion formula, by orthogonality of characters, our original sum will equal this average of these character sums. And so our main task is to evaluate these character sums. So to do that, we have the L function, which is the sum of chi of n times n to the minus s over natural numbers n, relatively prime to q. And the reason this is relevant is you can calculate formally the logarithmic derivative of the L function, and it is equal to the same sum now with lambda n inserted. So chi times lambda times n to the minus s. And then using this as a counter integration, we can extract the sum of lambda against chi over some integral by integrating this logarithmic derivative over a suitable contour. And then by contour shifting, we can give an explicit formula for this as a sum over zeros of ls chi. So we're using the fact that ls chi is a global holomorphic function. If chi is 1, it'll have a pole, and so we also have a term for the pole. So this technique can be applied most easily if we assume the generalized Riemann hypothesis. Because in that setting, all the zeros lie in the critical line, or there's trivial zeros to the left, and each one will have a contribution of size about x to the 1/2. And the total sum will be O of x to the 1/2 plus epsilon. At least for non-trivial characters chi. For trivial characters, the sum is going to be about x by the prime number theorem. So if we plug those two values in, this sum is x for the trivial character, and it's square root x for all non-trivial characters. We get this estimate that the sum of von Mankel projection in the progression is like x over 5q plus error term of size approximately square root of x. So this is a good estimate for q less than x to the 1/2 minus epsilon. For two reasons, or because the error term here will then be smaller than the main term. And if q is bigger than x to 1/2 plus epsilon, it's a bad estimate for two reasons. One is that the error term is bigger than the main term, and the other is the error term is bigger than the trivial bound you could get just by using lambda of n is equal to log n for all, or sorry, lambda of n is at most log n for any n. So this is not very useful for q greater than x to 1/2. So other than that, the main drawback of this estimate is it requires the generalized Riemann hypothesis. And so without the generalized Riemann hypothesis in the unconditional world, there's a few different things we can do. So the first one is Siegel-Wolfis, which gives some kind of estimate for q less than a power of log, an estimate where the error term is smaller than the main term. And this is using like non-vanishing results that are known about L functions in certain regions, and it's ineffective because of Siegel zero problems. And so this is often useful. And the other thing that's often useful is Bombieri-Vinogradov, which is an estimate in the same range as this Riemann hypothesis estimate for q less than x to the 1/2. At least it should be capitalized. Except it's not an estimate for a single q, it's an estimate for the average on many q. So the error term could maybe be large for one q, but if it's large for one q, it must be small for another q. This is very powerful, but sometimes you really need to go beyond this 1/2 power. And for that, our tool is the level of distribution estimates, which is a wide class of estimates that all have this feature that they're on average over q, and they allow q to be up to some power of x, which is greater than 1/2, but still less than 1. So it's like a half plus delta for some delta greater than 0, which is usually pretty small. And there's a lot of different estimates of this type, because you can do different kinds of averages over q. You can like put an absolute value or not. You can put a weight function. You can choose the same a for different modulus q or different ones. And you get different estimates in different cases. I don't really have time to go over all of this. Let me say that in a lot of cases, the best known estimates are in recent work of Maynard. So that's all I'm going to talk about the integer setting. I want to now talk about what we can do for the same question in some kind of analogous situation with polynomials or a finite field. And it turns out we'll be able to do a lot more. So we're going to fix a prime p, and we're going to fix the field fp, the integer is mod p. We could also take fq to be q to be a prime power, and then fq a finite field of prime power order. But I thought people might find integers mod p simpler. And the main object of study for us will be the ring of polynomials in one variable over fp, which we'll think of as a very close analog to integers. And this is an analogy that is used a lot in like number theory and also often in some other fields. And then instead of the natural numbers or positive integers in this setting, we can work with the monic polynomials. The polynomial is the leading coefficient 1, which I'll denote with a little plus there. And instead of working with monic polynomials of bounded size, we can work with monic polynomials of bounded degree. And just like in integers, it's often convenient to work with like a dyadic interval from x to 2x, throwing out integers which are too small and too large. Here we want to work with polynomials that have only a particular degree. So we'll write mn for polynomials of degree n. And we should think of this as being an interval of size x, where x is about p to the n, because it has p to the n polynomials of degree n over fp, and there's p to the n numbers in interval of sizes. And so the modulus that we're going to do, looking at progressions mod, will be a polynomial g. And for technical reasons, I want to always take g to be square free. And I'll write m for the degree of g. So the larger m will be, the larger our modulus is. And then let me write down the von Magellan function in this setting. The analog of log is degree. So we're going to say lambda of f is going to be the degree of pi if f is a power of a prime pi, and 0 if f is not a prime power for f a monic polynomial. So it's just the direct analog. And now let me give a statement. So the way you want to read this statement is you want to look at the last line first. So we're going to be summing over monic polynomials f congruent to a mod g, lambda of f, the von Magellan function of f. Exactly what we're doing before. And we're going to prove an estimate, which is like what we had before. We have this main term, p to the n over 5g. And then we have the error term. And the main term is of size p to the n minus m. So we'd like the error term to be smaller than the main term. And in fact, it's going to be smaller by a power savings. We'll write it as O of P to the M minus M to the 1 minus delta. And then the condition under which we can prove this will be some inequality between P and theta, where theta is the ratio here between the degree M of G and then the degree N of our polynomials. So theta will be the analog of the exponent, that if Q is a certain power of X, that power would correspond to theta here. And so what we need for this estimate is P is greater than this formula, 4 to the 1 over 1 minus theta, 1 over 1 minus theta minus a half squared times E squared. So E is 2.718. There's not a hidden variable E here. And in this, under this inequality, there's going to be some delta, so that for any natural numbers n and m, any modulus of degree m square free, and any invertible residue class mod g, we get our desired power saving estimate. So the level of distribution theta we can take with this estimate is going to grow as P grows. As P gets larger and larger, it's going to get closer and closer to 1. In fact, we already get better than 1/2. So theta in 1/2 in this setting would be what you can prove using only the Riemann hypothesis. And we can do better than that for P greater than 66. So P does not even have to be very large for this estimate to kick in. And furthermore, the amount of power savings we get is actually pretty large. So it's given by this explicit formula, 1/2 minus log P of some weird looking function of theta. And so what that means is that if theta takes any fixed value, as P grows, the amount of power saving is going to converge to 1/2. So as P gets larger and larger, the level of distribution is going to 1, but it's not just asymptotic. We get power savings and it's converging to square root cancellation. That's why I put square root cancellation in the title of the talk. A prior work I want to mention is in an earlier joint work with Sawin, we had a similar estimate on sums of Von-Mangelin progressions. This was in the case of a finite field of prime power order, and we have this inequality involving P, which if you try it for any value of theta greater than 1/2, you'll see it's a worse inequality. It's a lesser range, and it only works for theta up to just a little bit greater than 1/2, or else this will blow up. But it did have one advantage, which is while we didn't write that proof in the non-square free setting, the proof could be generalized to the non-square free setting, whereas this proof I still don't know how to generalize to the square free setting. Does anybody have questions about this statement? Leaving.
There is a question in the chat. I'm not sure, Will, if you can read it.
Yes, exactly. So that is exactly the condition to make delta positive. Yeah. Yeah. So P yes. P satisfies this inequality if and only if this delta is positive. And that's what come from. So the method gives you an estimate, which is a power savings estimate if P is greater than this range, and is a power loss estimate if P is less than that range. And I just don't write down that estimate because it's totally useless to have an estimate here with a power loss. Cool. So what I want to move on to after this, there's kind of a big main theorem which is underlying this result and applies to kind of other sums. And what I want to move on to is an application of this main theorem, which I like because it involves an interesting argument, and I like because it also shows the level of generality that's available. And then once I talk about the second application, I'll try to actually explain the main theorem. And so the idea of this is that a prime number or a prime polynomial is a number or polynomial with a very special factorization. It has one single large prime factor. And so what we show is that they have these polynomials have the same frequency in arithmetic progressions as they do overall. But there's many different kinds of factorizations of polynomials we could look at in terms of like what are the degrees of their factors. And then we can ask, do all these factorizations have pretty much the same frequency in the progression as they do overall? And so and that's the question I'm going to give a partial answer to. And to make this answer precise, I'm going to use a notion which is introduced by Gordetsky, which is this idea of an extended factorization type of a polynomial. And so the way this works is we take our polynomial f, we write it as a product of distinct primes raised to powers, and we'll just keep track of what are the degrees of those primes and what powers do we raise them to. So we're going to keep track of the set with multiplicity of ordered pairs, degree of pi I and ei. And that will lie in some kind of finite set in the set of all sets with multiplicity of ordered pairs, where the sum of the products of the ordered pairs sum to n, just because the sum of the degree of pi I times the exponent will be the degree of f, which is n. And so we can try to understand the distribution of the extended factorization type of f in progressions. And then maybe a warm-up, we should think about the extended factorization type of f for just f an arbitrary polynomial of degree n, like random polynomial of degree n. And this is a question which you can answer. You can describe this distribution using the prime number theorem, counting primes. Every polynomial is a product of prime factors. You count how many choices there are for each prime factor. That gives you a formula for how many choices there are of a polynomial with a given factorization. If you want your polynomial to be prime to g, all you have to do is subtract off the prime factors that are also prime divisors of g from this count. So this is a relatively straightforward question. What do the factorization types of polynomials look like? You can ask sort of very complicated questions about these factorization types that might have a hard answer, but I want to think about this as a basically known distribution. But the second question is harder. The second question is, what is the distribution of the extended factorization type of f? You take f to be a random polynomial of degree n, which is congruent to some fixed residue class A mod g. And this you can't answer using just the prime number theorem. You have to understand how different kinds of polynomials behave in progressions. And so the result I'm going to give on the next slide is a bound for the difference between these two progressions. And we're going to do this. We're going to keep a lot of the notation from the previous theorem. So we're still going to have polynomials of degree n, g, a square free modulus of degree m should be less than or equal to theta n for a real number theta, and we'll have a residue class mod g. And we're going to write down two probability measures. The first measure is going to capture the behavior of a random polynomial congruent to a mod g. So for each polynomial of degree n congruent to a mod g, we'll take a delta mass at its factorization type omega f. We'll sum those, and then we'll divide by p to the n minus m, the total number of such polynomials. And then we'll do the same thing for polynomials which are just relatively prime to g. We'll take their delta masses, sum them, and divide by 5g times p to the n minus m, which is the number of polynomials of degree n relatively prime to g. So these two measures, and I want to show they're similar by bounding their total variation distance, which is like the simplest distance you can write down between probability measures. It just measures the sum of the differences between their probabilities. And so what I might like to prove is that this difference goes to 0 as n goes to infinity. But I didn't quite prove that. What I instead proved is this difference is at most a term that goes to 0, plus another term, which depends only on p and theta. So this term, it has a kind of funky formula. It depends on this variable L, and L, if you view it as a function of p, is like a small power. We have a root p here, and then we're raising it to 1 minus theta. And then as a function of L, here we have this L to the L in the denominator. That grows super exponentially. In the numerator, we have e to the 2L, L to the minus n over 2, L to the 9 over 2. Those grow polynomially and exponentially. So this denominator is going to dominate for L large. This is going to be going to 0 as p goes to infinity for any fixed theta. And so we don't know that the distributions agree exactly, but for p large enough, we know that they agree like to 99% or like 99.9%, or any number of nines you want. So just in terms of numerics, you need, like, for theta around 1/2, you need p to be about like 1 million to start getting like an interesting estimate like this. And then once p increases to like 10 million or 1 billion or 10 billion, then you really start getting like a high quality estimate where the secondary error term is like really pretty small. But it never quite goes to 0. And so there was prior work in this direction by Gorodetsky in the case where theta was at most 1/2. So this is the case where you can try to prove it using just the Riemann hypothesis as your tool. It's like the Riemann hypothesis range. And in this case, he was able to get a much stronger estimate, which really goes to 0. He didn't have the secondary term, and in fact, he could control how fast it goes to 0. And so the existence of the secondary term is like an artifact of the combined difficulty of like going beyond Riemann and also studying every factorization type at once. Does anybody have questions about this statement? Well, if you do, feel free to ask at any time, because I don't mind being interrupted at all. Let me start talking about the proof of this statement. So the strategy I'm going to use is to bound, to work with one factorization type at a time. And we're going to bound for each type the amount, the frequency of that type can decrease when we restrict from all polynomials prime to g to a progression. And so we're taking advantage here of the fact that the total amount of decrease is equal to the total increase because mass is conserved, and we're only going to bound the decrease. And then a way that you can think about the counting polynomials of particular extended factorization type is by using convolutions of copies of the von Mangel function. Because if you have if you count polynomials which factor into 1 prime of degree 7 and 1 prime of degree 10, you can take the von Mangel function, restrict that to polynomials of degree 7, take the von Mangel function, restrict it to polynomials of degree 10, and convolve those two restrictions. And you'll get a function which is mostly supported on polynomials of degree 17 with that factorization type, and then a few other polynomials in which are kind of not so hard to sieve out. And these convolutions of restrictions of the von Mangel function are going to be much nicer for me to sum. And so we have to do some sieving to get things into that state. And then I'm going to use some kind of main theorem, which for now I want to be a black box, but it's proven by some kind of geometric method, to bound sums of the von Mangel convolutions in progressions. And that theorem will give me a bound with a main term, which is the sum over everything prime to g, and an error term. And the error term is going to be given by some formula, which is sometimes a power savings and sometimes a power loss. So in the case where it's power savings, it's like, great, I have a very small error term. I can, absorb all those into the little of 1. When it's power loss, I can't use that estimate. I have to do something else. And the thing, it turns out, that determines if it's a power saving or a power loss is this notion of the entropy of a factorization type, which is like the entropy of like a probability distribution with like probability log like a over n for each like term a, meaning for each like prime factor of degree n. Sorry, probability a over n. And so because the probability is a over n, we have this a over n log a over n, and then it occurs multiplicity b, and then we sum, and there's a minus sign. So this is the notion of the entropy. And this L formula I wrote down is the cutoff. Below that entropy, we get a power savings below log L, and above log L, we get a no useful bound. And so what we're going to do for a factorization type with entropy greater than log L is use the trivial bound. The frequency can't decrease to less than 0. So it cannot decrease by any more than its starting frequency. So the second part of our error term will come from the total frequency of all these high entropy factorization types, or equivalently, the total number of polynomials of entropy greater than log L. So let's now focus on this problem. And this problem I'm going to solve now by an entirely elementary method. I'm not going to use any geometry. And because of this, the proof would work almost the same for factorizations for entropies of polynomials and entropy of numbers. So let me just rewrite the definition of entropy for polynomials and for numbers. So for the entropy of a polynomial, if I can write it as a product of prime factors pi I, is going to be the sum of degree pi I over degree f times log degree pi I over degree f over all pi I with a minus sign in front. And so similarly, the numbers, the entropy of a number, I want to say is sum over prime factors pi of log pi over log n times log of log pi over log n with a minus sign thrown in front. And so we can ask how many polynomials or how many numbers are there of high entropy. And there's a very natural tool to try to use to study this problem, which is the limiting distribution for the sizes of prime factors of a random polynomial or a random number, which is called the Poisson-Dirichlet process. Terry Tao has a great blog post. You can read about this if you want to learn more about it. I'm going to quickly summarize it. The way this random process is defined is you choose your first random number y1 uniformly between 0 and 1. Then you choose y2 uniformly between 0 and 1 minus y1. Then you choose y3 uniformly between 0 and 1 minus y1 minus y2. You repeat, you get an infinite sequence of non-negative real numbers summing to 1. And then this sequence y1, y2, etc. is the limiting distribution of degree pi 1 over degree f, degree pi 2 over degree f, and so on. And I mean that in two senses. One is that it's the limiting distribution for like unordered sequences with a particular natural topology. And the other is it's a limiting distribution of ordered sequences if you order the degree pi I over degree f in the right way, which is a certain random order. So that then we can check that to bound the probability that a number or a polynomial has high entropy, it suffices to bound the probability that this Poisson-Dirichlet variable has high entropy. That sum I yi log yi with a minus sign in front is greater than log L. And it isn't completely formal because this function is not actually continuous along the topology that it's like the limiting, proven to be the limiting distribution on, but you can prove that it's like closely approximated by continuous functions, and then it's fine. So we've reduced it to a problem entirely in probability theory of how to understand large values of this random variable. And one thing you could do, you could calculate the mean and the variance, use that kind of estimate. You wouldn't get a very good bound. And so I'm going to explain how to get a bound which is much better, and I think is relatively close to sharp. And so the idea is to view this process kind of in reverse. Think about this where we choose, think about it as a process where we choose the first variable last. So we're going to define a Markov chain where we take a sequence of non-negative real numbers summing to 1, and then the next step will be a new sequence of non-negative real numbers summing to 1. And the way we'll do that is we'll choose a random x from 0 to 1, and then we'll make that the first entry, and we'll shift all the other entries 1 to the right, and we'll multiply by 1 minus x. And so it's sort of clear from the definition that if you run this Markov chain long enough, you'll converge to the Poisson-Dirichlet distribution. It's the unique stationary distribution. And so it suffices to look at how the entropy behaves under this Markov chain. And you can write the entropy after applying this step in terms of the entropy before, so the entropy itself forms Markov chain. And it turns out the entropy behaves really nicely under this process. So the most important fact is that the exponential of the entropy increases by at most 1 when I do this step. And if you think about the exponential of entropy as like the number of possibilities, given that we're only really adding one possibility here, we're adding a new possibility at the beginning with probability x, this should maybe be intuitive. And so, but it usually doesn't increase by at most 1. If the starting entropy is large, it's likely to decrease. And the higher the entropy, the more likely it is to decrease. And we can use those estimates to understand, to approximate this chain with a simpler chain, which will be easier to understand. And so the idea is we kind of round the exponential of the entropy up to the nearest integer value. And then we look at how likely it is to increase, and we make our new chain increase by exactly 1 whenever the previous entropy was going to increase. And we make it like decrease by 1 whenever the previous one was going to decrease by at least 1. And then we'll make it say the same any other time. And so this one will always be increasing faster. Our new chain will always be increasing faster or decreasing slower than the original one. So its entropy of its stationary distribution has to be higher than the original one. They're kind of coupled together in this way that lets us do that. But because we define our new chain to be an integer valued and only increase by 1, stay the same, or decrease by 1 each step, we can solve for the stationary distribution exactly. We get an explicit formula, and then we can just easily calculate the probability of being greater than a particular value. So using that bound, that gives us this weird function of L, and then we use that to bound our original chain, and we plug that in, and it gives us this error term. Okay, so now I want to say a little bit about what is the kind of algebraic statement that you can specialize to these different things. And so I'm going to go back to looking at things a little more classically, not looking at things probabilistically, but looking at things in terms of summing arithmetic functions. And the kind of arithmetic functions I'm going to sum are functions of a polynomial that depend only on the degrees of its prime factors. And so you can think of them as being analogues of functions of an integer that depend only on the size of its prime factors and depend only very smoothly on the size of the prime factors. So there's a lot of interesting arithmetic functions in this type. There's a von Mangold function, which we already talked about. There's a Mobius function. There's a divisor function. There's also more complicated ones. You can look at the indicator function of y smooth numbers. You can look at the degree of the largest prime factor of a number. You can look at the max over n of the number of divisors of degree n, and you can come up with weirder and weirder things. So in the function field setting, we try to do something which would be very bizarre to attempt in the integer setting, which is to prove a single theorem which holds for all these functions at once. It's kind of the penance we have to do in return for the function field setting be a lot easier. We try to make up for that by proving many theorems at once. So to do that, I want a nice formalism that encapsulates all these functions, or at least a lot of them. And that's what I'm going to spend the next couple slides doing. So I want to find a nice basis for the space of arithmetic functions. And so the way I'm going to do this is by starting with defining my functions on square-free polynomials and then extending them to non-square-free polynomials. Which is part of the general philosophy. If you can get things right on square-free polynomials, then you're usually correct overall up to, maybe have to do some kind of step. But usually it's better to understand the main terms. The square-free polynomials are the most important part. And so for the square-free polynomials, we're just going to be looking at the degrees of their prime factors, which form a partition of n. So the functions we care about can be viewed as functions on partitions of n. And there's a very nice basis for the functions on partitions of n, which is provided by representations of the symmetric group. So to fit the title of the seminar, I'm calling this Fourier analysis on the symmetric group. So where rho is any representation of the symmetric group, most likely we'll take it to be irreducible. We can define this function f rho, which is going to be the trace on rho of a permutation sigma, which has one cycle of size d for each prime factor of f of degree d. And so by basic theorems in character theory, this gives us a basis. So we can express any function of partitions in this way. And so then we want to extend these functions f rho from square-free polynomials to non-square-free polynomials. And it doesn't really matter how we do this, any kind of choice we can sort of go back and forth between, but I'm going to choose the choice that gives really nice formulas, and it's also sort of geometrically very nice. So the most obvious thing we could try is use the same definition as for square-frees. We can treat the repeated prime factors as if they were the same as two different primes that just happen to have the same degree. And so there are a lot of arithmetic functions that work like this, like the Liouville function, the indicator function, the primes, or some exponential in the number of prime factors. But there's another approach we can take, which has many different definitions, and you can sort of tell it's very natural because it has so many different definitions. But none of the definitions is 100% simple. They're all a little bit strange. So one expression of this that connects to what I was doing before is we're going to take the unique extension of f rho that can be obtained as a linear combination of restrictions of the von Mangold function to polynomials of a particular degree. So if I restrict the von Mangold function to polynomials of degree 4, restrict to polynomials of degree 7, restrict to polynomials of degree 8, and then convolve those three functions, I'll have a valid arithmetic function of polynomials of degree 19. And there's a nice algebraic formula for this, or probabilistic, which is you take each of your prime factors that occur with some degree d and some multiplicity m, and you generate a random permutation in Sn. So if multiplicity is 1, we're not doing anything, it's just a trivial permutation. For the higher multiplicity, we're generating some kind of interesting random permutation, and we want these to all be independent. And then you take this permutation, you multiply all the cycle length by d, the degree, and you concatenate them. When you concatenate them, you get a polynomial of degree, the sum of d times n, or you get a permutation of size, sum of d times n, which is n. And so you can let f rho of f be the expectation of the trace of that permutation on rho. And so this weird little algebraic formula, if you try it for some different representations, you get the Mobius function to pop out of the sign representation. You can get the von Magellan function to pop out. You can get the divisor function. And it's equivalent to the definition I gave before. It's equivalent to a bunch of other definitions too. And this tends to lead to the really nice formulas. And this form was studied by Haas and Mattei, and also in a slightly different context, studied by Kadish. So that's what I'm going to use. But if you just pretend I'm using the other one, it won't be too far from the truth. So before I talk about what we can get from a geometric method on this problem, I'm going to talk about what we can get by this more classical method of doing Fourier analysis on the multiplicative group and studying L functions. And the reason I'm doing that is because certain formulas will appear in this setting, and then the same formulas will reoccur in a slightly different way in the main geometric theorem. And so I'm hoping that going over this will be helpful for understanding that. So the thing we're trying to estimate, we defined our functions f rho, which might be the divisor function or the Mobius function, or it might be some stranger function than that. And we're trying to estimate the sum of f rho in a progression of polynomials congruent to A mod G for a square-free polynomial G. And the first step we're going to try is to write this as an average over characters of the sum of f rho against the character chi times chi conjugate of our residue class A. We can do this again using the Fourier inversion formula. And then we want to express this sum of f rho against chi in terms of the L function. The L function in this setting is the sum over f monic chi of f times p to the degree of f, p to the minus degree of f times s, or p to the minus nf, where n is the degree of f. And from this expression, you can see it's a power series in p to the minus s. And in fact, as long as chi is non-trivial, it's a polynomial in p to the minus s. It's a polynomial degree m minus 1. And so you can write it as a product, its constant term is 1, so you can write it as a product of 1 minus alpha I p to the minus s for some complex numbers alpha I. And so my claim is that using like the definition of the L function, you can express the sum of f rho against chi in terms of the alpha i's as a polynomial function of the alpha i's. And in fact, for rho and irreducible representation, this is going to be a very classical polynomial to study. It's a sure polynomial. It's going to be a character of an irreducible representation of the general linear group arising by Schur-Weil duality. So let me try to say that concretely, although slightly messily. We can make a representation of GLM-1 from rho by taking this m-1 dimensional vector space that GLM-1 acts on, taking the nth tensor power, so the symmetric group Sn acts on it for meeting the factors, and then tensoring with rho and tensoring with the sign representation of the symmetric group, and then taking Sn invariance. And I'll call this V rho. And my formula for f rho against chi in terms of the L function will use the character of this representation V rho. The trace of V rho evaluated at a diagonal matrix whose diagonal entries are alpha 1 through alpha n minus 1, the variables, the roots appearing in our formula for the L function. And this formula implies a nice estimate on this character sum. We're going to use the theorem of Weil that the Riemann hypothesis, which says in this setting, the size of the alpha I is at most root p. And then if you look at the eigenvalues of this diagonal matrix on V rho, they're all products of n of the alpha I. So they all have size at most p to the n over 2. Since the eigenvalues have size at most p to the n over 2, the trace is at most p to the n over 2 times the dimension of V rho. And then if we apply this for every non-trivial chi, we get the sum of f rho that we care about minus the main term, which is the contribution of the trivial chi, is also bounded by p to the n over 2 times dim V rho. So this gives you an estimate of similar quality to the Riemann hypothesis estimate we wrote down earlier in the von Mango case. It's of size roughly square root of the length p to the n of the interval that we're working in. The only difficulty in this is this dimension V rho. Depending on your choice of rho, dim V rho could be relatively large. So this argument I'm giving is roughly the approach that was taken by Gorodetsky to count these factorization types in progressions, except that he had to do something more clever than just using dimension of V rho here. He had to use other properties of the L function to get a better estimate, just like we often do in the integer setting, it turns out. And then another thing that I want to bring up, because it will be helpful to understand this main theorem in the end, is the case of the trivial character. I want to give the same formula in the trivial character, even though we were previously happy to take the trivial character, just make that the main term. So the L function in the trivial character is not going to be a polynomial. So I've written this L function in trivial character in such a way that it doesn't include its sum of p to the minus ns, but only over polynomials prime to g. So if we wrote this as an Euler product, it wouldn't include the Euler factors at primes dividing g. If we included those Euler factors, it would be the zeta function of fp adjoint t, and the zeta function is 1 over 1 minus p to the 1 minus s. So it has a single infinite chain of poles. And then we get some trivial zeros, that come from the missing Euler factors, and they'll have the form 1 minus alpha I p to the minus s for alpha I from 1 to m. For I from 1 to m, where the alpha I will all be, turns out, roots of unity. And so we get a similar but slightly more complicated formula for f rho in terms of these alpha i's. It's going to be a sum of, from an alternating sum from d equals 0 to n of p to the d minus 1 to the d times the trace of some diagonal matrix with entries alpha 1 through alpha m on the dth representation in some sequence, where the sequence is defined by you take rho and you restrict it to symmetric n minus d times symmetric d. You take the n minus dth tensor power of an n-dimensional vector space. You take the sign representation only on the s n minus d factor, and you tensor those all together before taking s n minus d times s d invariant. And that produces a representation I'll call V rho. And so let me now state a master theorem, which is going to be an estimate for the sum of f rho in an arithmetic progression with square-free modulus for arbitrary rho. And it's going to be stated in terms of the characters of these two representations. So I have two terms, and the way I'm going to get these terms, these c's, is by taking this character, and instead of plugging in the roots of the L function, I'll plug in formal variables, lambda 1 through lambda m minus 1. And then I'll differentiate it in each of those variables, and then I'll set the variables equal to 1, and that produces C2. And then to make C1, I take V rho D, I look at a diagonal matrix with formal entries, I differentiate in each one, I set them equal to 1, I do some alternating sum, and then I subtract some factor which involves the dimension of VD rho and involves binomial functions. And so the theorem I can prove is that for any natural numbers n and m with n greater than or equal to m, for any square free G monic of degree m, any residue class A mod G, and then any representation row of Sn, the sum of f row of f in the progression A mod G minus the main term, 1 over 5G times the average of f row over all progressions relative to prime to G, is bounded by this square root cancellation term, p to the n minus m over 2, times this c1 plus c2 root p times a little constant factor of 2. So this is going to be an estimate, which is always going to approach square root cancellation as long as c1 and c2 are not growing too fast as a function of n and m. And you'll for nice arithmetic functions like the Mobius function, the divisor function, you'll find that happens when m is less than some fraction of n and p is sufficiently large, just as in the von Mangel estimate. Does anybody have questions about this statement?
There is a question in the chat.
Oh, to repeat the definition of f row of f. So f row is defined by, on square frees, you take the permutation, which is one cycle of size d for each prime factor of f of degree d, and you look at the trace of that on row. And then you extend it in the best possible way to the non-square frees, which turns out to be given by this weird definition with random permutations. Or you can also say it's the unique extension. It's the sum of convolutions of the restrictions of the von Mangel function to follow in a particular degree. It also works, by the way, if you take the sum of restrictions of the constant function to von Mangel to follow in a particular degree. Or it works if you take the sum of restrictions of the Mobius function to polynômials of a particular degree and involve those. So for example, if rho is sine, this will get you the Mobius function. This will get you a Mobius estimate for rho, the sine representation. And if you want an estimate for the kth divisor function, you can take the nth tensor power of a k-dimensional vector space, choose that to be rho, and this will get you the kth divisor function. So those are some examples of how you can get different functions out of this estimate. So if you literally choose a typical irrep, then I think C1 and C2 are going to be just enormous. They're going to be potentially much bigger than an exponential in n. And that's because like the dimension of a typical irrep is also enormous, and the dimension of the Scherweil dual of a typical irrep is also enormous. So what saves us is the ones we care about for things like Mobius function, divisor function, von Mangel function are actually very far from typical irreps. If you express their partitions, they have a few very large parts and then many very small parts, but like no medium-sized parts at all. And those we have much better estimates, which will typically be exponential in n. And then so the key thing is also that the ones we need to count low entropy factorization types are also the dimension of the irreps and the corresponding like size of C1 and C2 are relatively controlled by an exponential n. I mean, so maybe one thing I should say is that you can see C2 can't be that much bigger than the dimension of V rho, because you can just look at what's the largest possible value for this derivative of any monomial of degree n and n-1 variables, and that's a bound for the ratio of C2 to 0. So if you want to understand how big these are, the first thing you want to try is to understand 0. So let me say something about how I can apply this. I certainly don't have time to state all the applications. But you can get from this estimates for sums of the main arithmetic functions of interest, the von Mangold function, the Mobius function, the divisor function in arithmetic progressions. And they're roughly similar to the estimate I showed you for von Mangold. Using the divisor function estimates, you can get some kind of moment estimates for the Dirichlet L functions LS chi. Using the von Mangold estimates, you can get one level density estimates for the Dirichlet L functions LS chi. And then the main thing to get these estimates is to calculate C1 and C2. And what you end up doing is manipulating some generating functions that tell you about the characters of these representations and then taking their derivative. And when you're manipulating the characters, the manipulations you have to do often correspond to exactly what you would be doing if you were trying to solve the same problem using characters. So for the divisor function, you would consider powers of the L function the character, and so you would be writing you would end up writing powers of a certain polynomial and taking the derivatives. For the Mobius function, you would end up considering inverses of the L function. So here we would take inverses of a certain polynomial and take the derivative. And so there's kind of a nice synchronicity with the more classical method. So there's a ton of prior work on these problems, at least over the integers. And I also don't want to have time to review it all, but I wanted to mention that some of the strongest results on some of these problems were due to Zacharias and Drapeau, Pratt and Radziwiłł, and Maynard, Cooley, Linnick, and Selberg, Fourier, Kowalski, Michel, and Fourier, Radziwiłł. And then on some of these problems, Mark and I had prior work in the finite field setting. Okay, well, yeah, let me stop here, and I'm not trying to do the last little thing. So okay, it's proven by geometry, and I didn't find a way to make it the proof really accessible enough to talk about, which is why I'm not really talking about the proof of this main theorem. Thank you for inviting me to speak. Thank you for organizing this lovely seminar. It's been a great summer.